Hey y'all, this is the video for the Monday class for the Oaks. I'm going to be going over a couple different things for y'all, just so just for people who are either in chapter 17 and 19 or around chapter 60. I'm just going to be going over some parts for that. It's a couple of problems. So for whoever's up higher in the lesson, I'm going to be going over chapter 60. And then whoever's lower, I'm going to be going over chapter 20. I believe we had two people that were 17 and 19. So we'll look at chapter 20 just so we have a little bit of knowledge going into that if we don't have a chance to go over it before I actually can lecture or before I can actually tutor for that day. So first thing, in chapter 20, we're talking about two things: simplification of radicals and line parallel to a given line. So let's talk about simplification of radicals. So first of all, what is a radical? That's, I think, where we should start with that. A radical is a number or a variable underneath a square root sign. So square root of 2 is a radical. Square root of m is a radical. Square root of 2m is a radical. These are all radicals. Don't be thrown off by the name radical. That's all it means. It's just the square root of a expression. We know a couple of square root properties, at least here are a couple of square root properties. And just talking about addition or subtraction, we have square root of 2 minus square root of 2, that's 0. We have 2 times the square root of 2 minus the square root of 2, that's the square root of 2. You can just think of this as if square root of 2 were an x or a y, something that we wouldn't want to necessarily solve because square root of 2 is irrational. But if we have 2x minus x, there's 2 x's here and there's 1 x here, that's 1x. So it's the same kind of thing we're doing here. Same kind of thing with addition. Just throw a 3 in front because there's 3 square root of 2 is how I like to think about it. But when we're doing simplification of radicals for multiplication or division, let's look at multiplication first. So the example they use in the book is they say square root of 10 is equal to the square root of 2 times the square root of 5. Now, there's some things going on behind the scenes that I want to look at first. So if we look at the square root of 10, first of all, what is 10? If we break up 10, there's a couple different ways we could say. We could say 10 times 1. We could say 2 times 5. We could even say something like, 4 times, what would it be? 10 over 4 or 5 over 2, something like that, or 2.5. That's what I was trying to get. There we go. So there's a bunch of different ways to represent 10, and so we can actually break up 10 into something like 2 times 5, and that's the same thing. I think y'all can agree with that. 2 times 5 still underneath the radical sign, and what they're saying here that you can do is the product of square root. I'm going to write it out. Product of square root. I'm going to do this theorem just to save it some time. And all they say in this theorem is that, according to the book, it says, yep, if m and n are non-negative real numbers, so the only reason they can't be negative is because you can't have a negative under a square root. So if I had negative 2 under a square root, I can't have this number underneath the square root unless I'm able to represent it with an I or something like that, where I is equal to the square root of it. We'll get into that later, I'm sure. But for now, just assume that we're not going to have a negative underneath a radical. That would not be something that we're looking at. And that makes sense because let's say we have the square root of 4, right? What does the square root of 4 actually mean? Well, the square root of 4 means any two numbers, any number that can multiply itself twice give me 4. Now, is there a number that can be multiplied by itself twice to give me negative 2? Or let's say it was negative 4. That's a little bit easy. Well, you might think, oh, well, I can do negative 2 times itself, but negative 2 times itself is 4. And so there's no number besides an I equals square root of negative 1 that satisfies this. So let's assume that we can't use negative numbers under square root signs. Erasing this. Okay, so assuming we don't have a negative number, we have a positive real number. You're saying that the square root of m times the square root of n they're saying you can combine these into mn. That makes sense, and kind of backwards too. And this is where I want to look at it, because we were talking about 10, breaking it up. If you have mn, or 2 times 5, so we let m equal 2 and n equal 5, then what would that give us? That would give us the square root of 2 times 5, which is 10. And so what they're saying we can do is they can break these up. We can take square root of 5, 2. The multiplication becomes almost like you can split it. You can take square root of 5 times the square root of 2, and this becomes the square root of 10. So you can just combine these two things. Now, here's, oh, I messed that up. Here's a quick disclaimer. You cannot do. That goes both ways. And this is the product of square roots theorem. Now, here's a quick thing that you cannot do. This theorem only relates to products. As you can see by the word products, I'm going to underline it. It's very important. Product. Oh, that's not. There we go. Product. Very important. This is not valid. That's not valid. You absolutely cannot do this. You might like that you can do this. You might wish that you can do this, but you'll never be able to do this. The addition does not carry over into being able to split these apart. Only multiplication. So that's a quick thing, or subtraction. That's a really important thing. Also, I might say quickly a word. They don't say anything about this in this theorem, I don't think. No, they don't. But you can also do division with this. That division and multiplication are both work with this. And I'll just give you an example. If you have m divided by n, that's the same thing as saying m over n. You can play around with this with a calculator just to figure out if this right here is really equal to this over here, but it is. I will tell you that, and that is kind of what they're going with that. Here's a problem from the book that they might throw at you, and something that just to use for this. They have 3 times the square root of 50. They explain this in the book. I'm going to work through it really fast. Square root of 50 minus 5 times the square root of 200. And you're thinking, oh boy, here we go. Well, looking at this first, you can't subtract these two because they're different. They're different variables. One approach we could take is we could figure out what the square root of 50 is. We could figure out what the square root of 200 is, and then we could solve it. But they use the word simplify, which doesn't mean solve. It just means reduce it down to something that's a little bit more simple. So let's look at how we could possibly do this. We want to get these two radicals as the same, so we can subtract them. And so here's what we're going to do. So first thing we're going to do is say we keep 3 times the square root of 50. This is how I'm going to do it. I don't know if the book is how it does it. We're going to recognize that 200 is 50 times 4, right? So you might see where I'm going with this at this point. So we have 3 times the square root of 50 minus 5. We're going to use the product of square roots theorem. We can split these up. Square root of 50 times the square root of 4. Now, what is the square root of 4? Let's put this over. Square root of 4 is 2, because 2 times 2 equals 4. So the square root of 4 is saying what two numbers multiplied by themselves will give me 4. It's 2. So we have 2 is the square root of 4. Write this again. We have 2. This is 2 right here. So 2 times 5 is 10. And boom, we have these two are the same. So we can actually subtract these guys out. That's -7 times the square root of 50. Now, you could stop here, but we're going to do a little bit more. We want to reduce this down to the smallest it can be. So let's factor down 50 real fast. The way I'm going to do it is I'm going to say, well, we can say, what is 50? 50 is 2 times 25, right? Let's -7 times the square root of 2 times 25, like that. What's the square root of, well, let's split this up first really fast. That product of square roots theorem. the square root of 25, what two numbers multiplied by themselves will give me 25? 5, because we know that 5 times 5 is 25. We have our answer 7 times square root of 2. I'm running out of space here. But you can see 7 times square root of 2 is 5. Let's move this here where I have more space. Kind of have more space. So 7 times 5 is minus 35 because you have a negative in the front times the square root of 2. Let's see if that's what they got. Yeah, that's what they got. So we have negative 35 times the square root of 2. So that's how you reduce something down like this. And I'll just go over quickly what I did. We have 3 times the square root of minus 5 times the square root of 200. We can't subtract these down as they are. We can't simplify them down because the square root of 50 minus the square root of 200. Remember how I said you can't combine them for addition or subtraction? Well, that's where this comes into play. You cannot combine them here. And so, I'm having trouble with this. So you want to get them down to where 50 and 200 are the same. So that's like, imagine where when I said these are variables, but we don't want to solve out square root of 50 because if you put square root of 50 into your calculator, I'm going to do it really fast. Show it. If you put square root of 50 into your calculator, square root of 50, you get 7.0710678812. I don't want to write down 7.07, whatever it is, all the way down. So I'm just going to represent it with square root of 50. And since I don't want to do that, I can technically imagine this as a variable, x, and this could be another variable, 200, the same kind of thing, y. And so when I have x and y, I can't say x minus y is the smallest it can be. And so square root of 50 minus square root of 200, by themselves, they're the smallest they can be. However, using the product of square roots, we can simplify 200 down into a smaller, into two smaller radicals. So what we did here is we said 50 times 4. 50 times 4 is 200, and we can split those guys up into 50 times square root of 4. Square root of 4 is 2, so we have 2 times 5 is 10, so this 3 times the square root of 50 stays the same, and we have 10 to the square root of 50, so you subtract them out, this, and then we're going to try to reduce this down because square root of 50, one way you can always tell that something isn't reduced all the way down is if it's a factor of 2, then that's a pretty easy way to tell that it's not factored all the way down, because oftentimes things will be a factor of 2. So 50 is obviously a factor of 2 since it's an even number. And when you do that, when you divide by 2, you'll get a different number. And a lot of times you'll get something like 2 times 25, or if it was 100, you get 2 times 50, and then you factor 50 down, you get 2 times 2 times 25. And then you get nicer numbers that you can deal with where you have 25 is actually a square root. Well, it's a square, so 5 is a square, or 5 squared is 25. And so then you get negative 7 times 2 times 25. And what I did is just split that up like we were talking about right there. Split the 2 and the 25 to make the 50 as before. Then I have a negative 7 times the square root of 2 times the square root of 25. Square root of 25 is 5, so 5 times 7 is negative 35 times the square root of 2, and that's what we try to answer. So that might be a typical problem. Don't be thrown off by simplify. Simplify doesn't mean solve, it means reduce down to a smaller form. And the reason why square root of 35 times the square root of 2 is a smaller form is, first of all, it's not 2. Well, you might ask, I'm going to clear this out. Y is, I'm just anticipating a possible question. I know I asked myself. 3 times 50 times 5 times the square root of 200, which is what we started with. And they say reduce this or simplify this down. I'm thinking, why do I have to simplify this down? Simplify. Is that so hard? Simplify this down? Why would I want to simplify this down? It already seems like it looks kind of nice. And y is negative 35 times the square root of 2 simpler? Well, I'll give you an idea. First of all, the square root of 2 can't be factored down anymore. That's as low as it goes. And so square root of 200, you can factor that down into the square root of 100 times 2, which factors down to square root of 50 times square root of 2 times square root of 2, which factors down into square root of 25 times square root of 2 times square root of 2 times square root of 2, which factors down to 5. And so it keeps going down. So there's a lot more things. And so, this is pretty complicated, but it actually kind of gets down to something nice because this is a 5 here. And these two can combine to make a 2, and then you just have square root of 2. So it does get nicer. regardless, square root of 2 is the smallest form. Your only way you're going to get smaller than that or more exact or precise is by using a calculator, and you don't want to use a calculator for the square root of 2 because it goes on to infinity on the decimal point. So that's one reason. Other reason is it's only one expression. It's not something subtracted by something else. So those are the two reasons why I would say this is more simple. And this is what the math book is going to look like or look for. So that's one problem that we can do. I'm going to look at one more really fast. It's a multiplication problem in the book. So we have 3 times the square root of 2 times 4 times the square root of 12. And they want us to simplify this times 2 times the square root of 3. And you might see, okay, this definitely makes sense why we need to simplify this, because we want to get it down to one term first of all. And there's a lot of things that we can multiply down to get it to one term. So let's do that really fast. Let's multiply all the non-radicals together, because everything can be multiplied together. We could write this as 3 times the square root of 2 times 4 times the square root of 12 times 2 times the square root of 3. We can totally do that. But let's just group everything together. We can say 3 times 4 times 2, just for the ease of your eyes, all times square root of 2, square root of 12, square root of 3, right? So 3 times 4 times 2 is 12 times 2, which is 24. Not bad. And let's use the product of squares to, or what they say, product of squares theorem, to put these all under one radical. So 2 times 12 times 3. And I'm guessing this is going to be nice. Well, let's see what this equals. 24 times the square root of 24 times 3, which is 72, right? 36 times 2, which is 60 plus 12, which is 72. Well, is 72 a square? Well, 8 times 8 is 64, 9 times 9 is 81, so 72 is in between there. There's nothing we can do here to get 72 to be one number like 8 or 9. However, what we can do is we can use a trick that we used at the beginning, where, remember how I said that you can kind of separate things by 2, because 72 obviously can be divided by 2. So let's look at that really fast. I'm going to go ahead and clear this out and write that down again. We had 24 times 72. Let's simplify this down, because 72 can be divided by 2, so we're not done simplifying yet. And I'll give another note on that really fast at the end. But for now, let's look at this. So 24 times, let's split it up, square root of 2 times square root of 36, right? Ooh, that's interesting. 36 is the square root of 6. Well, square root of 36 is 6, because 6 times 6 is 36. So since the square root of 36 is 6, now we have 24 times 6 times the square root of 2. 24 times 6, that's 120 plus 24, that's 144. So that's what you're looking at for that one. And so that's simplify all the way down, because square root of 2, as we said, is the smallest it can be. Well, the most simple form it can be in the 144. Obviously, you don't have to do anything with that. Get it reduced. So let's do a quick thing. If I had square root of 6, I said you can divide it by 2. And so you might think, okay, well, let's simplify this down. So let's take out the square root of 2 and take out a square root of 3. And then you're thinking, ooh, well, square root of 3, you're not simplifying that down anymore. Square root of 2, you're not simplifying that down anymore. So you're kind of stuck here. And so this is actually the most simple form that you can get, I would say. Your math book might want you to put square root of 2, square root of 3. I'm not sure how they're grading it. But if I was grading something, I would be fine with either of these. And I'm not grading your paper, so obviously my opinion doesn't really matter. But what I'm saying here is that square root of 6 is as simple as it can be unless you break it up into this. And why is that? And that is because this is actually, I feel, more complicated or less simplified, because there are two expressions, square root of 2 and square root of 3. So when you get into things like square root of 10, sometimes it's helpful, because if you had square root of 10 over square root of 2, it's helpful to break up square root of 10 into square root of 2 and square root of 5, because then the square root of 2 is canceled. So you kind of have to see that and look ahead a little bit. But for some things, if you just had square root of 10, it might make more sense just to write square root of 10 as it is, because though you could break it up into square root of 2 times square root of 5, you're not going to be able to get this into one number. You're not going to be able to make 5. 5 isn't the square root of 5 doesn't come out to one number. It's a decimal number. So you could write square root of 5 is, let's see, square root of 5 is 2.236. So you could say 2.236 times the square root of 2, but then you might as well just find out what the square root of 2 is, 1.414, and then 2.236 repeating times 1.414, definitely repeating. And so then you get into this kind of thing. Nasty, don't want to do that. Much easier to keep it as square root of 2 or times the square root of 5. And that's why I would say if you have, like, let's say square root of 20, and you break that down into square root of 4 times square root of 5, you see here, you can actually make this 2 times the square root of 5. And then you might think, oh, well, that's two things. Well, it's a smaller radical, first of all, and it's something that's a little bit easier to work with than the square root of 20. That's just a quick, if that doesn't make sense, it's all right. It's something really nuanced that you're just looking for when they say simplify. Most of the time, you're simplifying means trying to get the radical down as small as you can. That's the idea, is trying to get the radical as small as you can. So if square root of 2 times square root of 3 is better for square root of 6, then go for it. But that's just a word of caution. Nuance, a little bit weird. Let's also talk about lines parallel to a given line. This is something that's pretty important. Before I go into this, I'm going to talk about our form here, y equals ax plus b. This is the form of a line. This is a relationship between x and y, and that's really all a line is. You have a graph, looks like this. A line is a bunch of dots that look like this, and all related to each other, and they all have an x, and they all have a y. Oops, that's not an x, that's a y. It's my best. Y, well, that's bad. I can't look at that. There you go, y. And so this is a line like that. So that's line theory 101 on that right there. So that in mind, let's think about, I've talked about this before, so I'm not going to reinvent the wheel. But let's talk about what these mean. So this is obviously a y coordinate. This is an x coordinate. A is the slope of a line. So that's how much, you might remember slope m is rise per run. So if we have slope is rise over run, that's how much we go from this point right here. Just imagine a point. How much we go up, how much we walk across to get our next point. And then go again, and we can go back this way. Oops, that's bad. And we just keep finding new points to draw a line. Okay, so there's the slope. So if we have parallel lines, let's talk about parallel lines now. And B is where the line that you're talking about actually intersects the y axis. So when you can find that because you know that when x is 0, this entire term will go away because x becomes 0, and you have y equals b. And so that's where your y axis will meet your line. So that's B. It's called the y-intercept. So let's talk about parallel lines really fast. So if I have a parallel line, do my best to draw a parallel line. I have a parallel line like this. It's like a road. So if I have a parallel line and I go rise over run, let's look at the slope of this line. Let's go up this much, go across this much to this point on the line. There. There's a rise over run. Rise over run. Let's do the same thing on this line, assuming they're parallel, which they're not perfectly parallel, but start at the same point. That. So that to say, that's not a perfect picture, but you can see that those triangles are pretty close. And so, well, that's not why, but this is just let me back up a little bit. This is just a nice little picture that can help you maybe see that the slopes of parallel lines are equal. That's what I'm trying to make a point of. The slopes of parallel lines are equal. And that's very important. And it's easy to think about, actually. This is a better illustration. If I have a parallel line here and here, let's say I moved this parallel line, right? This line I have, I don't know if I can move it. I thought I could. But let's say I have this line that I draw here, right? If I move this line over, not perfectly parallel, but imagine if it were, this line would perfectly match that line. And this line would be much better on this one. But this line would perfectly match this line. Like I could line it up perfectly. So let's say I did that. The slopes would be equal, right? Because if I had a rise over run, imagine somehow that these two lines were exactly the same, because they would be if I could move them over. The rise over runs would be equal on both of them because they'd be the same line. So they have equal rise over runs, so they have equal slopes. So that's the point I'm trying to make. Parallel lines have equal slope, or yeah, equal slopes. So let's do an example that might clear it up a little bit. So let's see, they say find an equation of a line that's parallel to the line 2y. Remember, this is just a relationship between x and y. We want to find a line that's parallel to that line and passes to the point 3, 1. So x is 3y. So what we're going to do with this is, first of all, I want to put it in the slope-intercept form, which is the form that tells us the slope. So I want to isolate y. Let's move x over to the other side. Yes. Okay. And let's go y. Let's divide both sides by 2. X divided by 2 is 1/2 x. 2 divided by 2 is 1. So there's our slope-intercept form. So what can we learn from this equation? Well, what we can learn is we know that the y-intercept is 1. So that's where this line will cross the y-axis. It will go through this. And the slope is 1/2. So every time I go up 1 unit, I have to go across 2 units to get to the next point on the line. That's what that means. So we want to find a line that has a slope of 1/2. So it's not too bad, actually, to figure it out. You can say y equals, interesting, ax plus b. We know a needs to be 1/2 because a is the slope. Y equals 1/2 x plus b. And we really only need to find b now. So let's clear this out and do it. So we have our point. We know that this line has to go through 1. We have our equation, y equals 1/2 x plus b. To finish this out, we just need to find b, because that we'll be able to have an accurate understanding of this line if we can find b. So what we'll do is we'll plug in these values to this equation. So we know that when x is 3, y is 1. So let's put that in. Y is 1 when x is 3. And now we only have one variable. We need to isolate that variable so we can find it. We have actual numbers here. Let's do that. We have 1 equals 3/2 b. We subtract 3/2 from both sides. 3/2 is 1/2, by the way, just to make that clear. This goes away because 3/2 minus 3/2 is 0. This is 2/2 minus 3/2, which is minus 1/2. Yes, minus 1/2. See if that's what they got. Oh, that's not what they got. What did I do wrong? I messed it up. It should be minus 1 here, which makes a lot more sense now to me. So this is minus 1. It makes it a little bit easier, right? So we have, fix this. Don't want to make these careless mistakes. There we go. Easy one. So minus 1 minus 3/2 is minus 5/2. Not minus 1/2 because this is negative. This becomes b is minus 5/2. So we can write our equation out. Okay, and so we have y equals a was 1/2. That's our slope. X minus 5/2, or plus minus 5/2. But that's the line that's parallel to our original equation, which was y equals 1/2 x plus 1, and also passing through the line 3 minus 1, about 1. So there's a typical question that you might have, and that's how you go about doing it. So that's it for chapter 20. I hope that helps for y'all moving through here. If you have questions on that, let me know, obviously. I'm going to now look at chapter 60 really fast, so we can go through that really fast. Let's see. Chapter 60, direct inverse variation. So our okay, so direct and inverse variation. So first of all, direct and inverse variation are proportional problems. So we have something like let's say we have A. If it was directly proportional, we would have a constant K. That's not a variable. That's an actual one number that cannot change. It's B. So we would say that A varies directly to B, or A is directly proportional to B. A is directly proportional to B. And this is actually an equation of a line, which is interesting. Let's say we throw on a lowercase b here. We have a y equals a constant b plus intercept. And if we made the intercept 0, so it went through the origin, then that would be 0. So a equals kb. That's a line. And it varies directly because every time you move up 1 for A, you move across 1 for B. Or better yet, this is called a direct. That's not right, actually, because if K was 2, you'd move up 2 and only 1. So there. So that's not 100% accurate or accurate at all, really. But for direct variation, or for something direct, every time you increase A, you increase B. That's what I was trying to say. Every time you increase A, you increase B. No matter how much, how small, it's always going to increase. So when A goes up, B goes up. When A goes down, B goes down. That kind of thing. So let's say we throw a couple constants in here just to play with it a little bit. Let's say we make K minus. If we make B 5, A is minus 25. If we make B 6, A is minus 30. So A is not increasing, but it's moving in a increasing direction for negative. So this is still direct. And a lot of times you'll see a positive constant there, so you don't have to worry about that. But if we did a positive number, when A increases, B always increases. So if B is 1, A is 5. If B is 2, A is 10. If B is 3, A is 15. So it's always increasing with B. So that's direct variation. And this is something you could see where if you had a negative number, a negative slope, normally slopes go, this way. They go from left to right on the page. But a negative slope goes from left to right, so you go up. But negative slopes go from left to right. That's the same thing, but they go from high to low, and positive slopes go from low to high. And so that's what you would be looking for a negative slope. That's so bad, but that is a negative slope. And as you can see, as you increase B, so heading in the direction of the line, that's a positive slope, actually. Confused that, my bad. Here's a positive, or here's a negative slope. There we go. As you move forward for X, that's a B here. You move down for Y. But Y is still increasing in the negative direction as X increase in the positive direction. The K is what really matters. Regardless, that's what direct means. As A increases, B increases, whether or not it goes in the same direction, positive or negative, is still increasing. Inverse variation, on the other hand, we say A is equal to K over B. A varies inversely with B, or that A is inversely proportional to B. But what we're saying here is, make another constant here, 5 for B. As B is 5, A is 5. As B is 10, A is 1/2. As B is, 25, A is 1/5. And so you're getting lower like this. And so if you graph this out, the real part about inverse variation is the graph here. So direct variation, as we said before, is, or directly proportional, is a line, right? A equals KB. Inverse variation is for this one, as B is 0. I don't think you can actually do that, but let's say we don't have B equals 0. As B is 1 here, we'll make B 1, then A is 5. As B is 2, A is 2/5. As B is 3, A is 3/5. As B is 5, A is 1. And so you're going to have something that looks like this. It's actually a curve. That. It'll get down really small, really close to 0, but we'll never get there. So that's what inverse is. You have K always is on the top. I'm like 5. K is always on the top. And B is here. So as B increases, the denominator increases, A gets smaller, because a bigger denominator means a larger fraction. 1 over 100 is smaller than 1 over a million. If you have 1/5 of a pi, that's going to be smaller than that's actually 100,000. 100,000ths of a pi. That's a tiny slice. 1/5 of a pi is a pretty good slice, 20% of the pie. So here's where we find that if we increase B, we increase A, or decrease A. And the same goes for if you have a negative constant. If you increase B, you'll decrease A, it'll get closer to 0. I think that's one way to explain it better. For constants, regardless of if it's positive or negative, for inverse, A will be getting closer to 0. For direct, A will be getting further from 0. That's maybe a better way to explain it. Regardless, this varies proportionally. Inverse, this is what an inverse function is. Inverse relationship better. So let's look at what they say. So this is the word kind of problem. If they say, the amount of cars on the road varies inversely with the time or the age of the drivers inversely, that's how you'd write it. You can just go with the wording. Or they say it varies directly. You can say K times the age of the driver. So it's a word problem. That's what you'll see a lot of, and that's what they have before. Let's do a quick question, and then we'll wrap this video up really fast. So the number of boys in every class. So very directly. Another way I think about this is the ratio. The ratio is exact on both sides. So what they're going to do is they're going to say boys varies directly with girls. We're trying to find K, so we can establish some kind of a relationship here. And one way you can think about this too is if you subtract or divide G by both sides, you get this. And so the ratio of boys to girls is always constant. That's what I was saying before, ratio for this. But let's go ahead and put our number in and figure out what K could be. So we have boys in 8 boys in one room equals K times 2 girls. And it varies directly. So we can find K. K is 4. 4 times 2 is 8. So K is 4 for every case. So we can say B, our boys, varies directly, in this case, by a factor of 8 with the girls. So they ask, if there are 5 girls in another room, how many boys are in this room? So we can actually solve this pretty easily. Just substitute in 8 girls, or how many girls? 5 girls. Do the multiplication. 40 boys. Pretty nifty little tool there. Actually, I completely did that math wrong. This is 4, not 8. That's what I did wrong. So another thing to remember, put your thing in right. There we go. So it should be 20. There we go. We're good now. So 4 is K. 20 boys, every 5 girls. And that makes sense with our relationship. So that's a varying directly problem. Look at a very inverse problem. So all we can do is we write down what we know as they talk, or as they write down what they say. Example 60.2 says the number of revolutions per minute. the number of revolutions per minute, RPM, varies inversely as the number of teeth in a gear. So we put our constant down and we say number of teeth. We'll use the same. Say number of teeth in the gear. There's our equation, just like that. So they say if 40 teeth result in 100 RPM. So we have 100 RPM, 40 teeth. What would be the RPM if the gear had 30 teeth? And so what you do is you solve for K, you multiply both sides by 40, trying to isolate K, 4,000 equals K. You put that back in our equation. We have our actual full equation now. 4,000 per of teeth. So we can solve that for RPM when there's 30 teeth. That's what the next question asks. So we substitute this in for 30. This is when NT is 30, right? So RPM, ooh, that had a P in it, equals 400 over 3, which is 1, 3, 3, 1/3. 133 and 1/3 RPM per 30 teeth. And then this is the important part. This is the equation. You can do anything with this equation you want. You can solve for the number of teeth with the RPM. You can solve for the number of RPM with the number of teeth. That's our equation. That's what they mean when they say inversely. So that's not too bad, right? So let's just summarize what we talked about with direct and inverse. So direct is A equals KB. It's direct. And A equals K over B is inverse. We saw how those two differ. We saw how we would attack the problems. Don't freak out about the problems that you're doing when they ask you a question. Word problems are a lot of times pretty intimidating when you do them. Don't be freaked out by them. Just see what they say. If they say A varies inversely, you write this down. They say, the number of raindrops varies inversely. I'm making this up. Number of raindrops varies inversely with the number of clouds. You say raindrops varies inversely with clouds. Boom, got it. If they say directly, rain varies directly with the number of clouds. Write that down and then plug your numbers in that they'll give you and find K. And there might be some variations of that. You'll have to be a little bit creative, but that's how you want to approach these problems. You just write down exactly what they say. Think about it in terms of direct and inverse, and you should be good to go. All right, I think that's all I have to talk about for today. Thank you guys for listening. I hope you all got a little bit out of it. Again, if you have any questions, email me. I gave you my email. Let me write it here. Give you my email address. Ask me questions, please. I'll try to put a little bit more of these videos out there in the future, just so we have them. So you can look at them. Don't have to look at them, but if they do help, then that's the goal. So I'll see you guys next time.